I'm not sure tomorrow. Tonight we'll have this project discussion session here at 7 o'clock. I think he wants to put a poster up again as well. Sid, take it away.
Okay, well, thank you very much. As you said, this is the last full day of lectures. And so I think it's appropriate that we really thank the organizers for having put on this summer school that has been fascinating and covered a wide range of areas. And I think introduced a lot of us to a lot of new topics and a lot of new friends and colleagues. And so I think this is a wonderful thing. And what I also want to point out that this summer school has been going on for 22 years. And this is not a small thing. And it's trained generations of students. And I didn't completely realize what an impact this has until people in my lab keep coming in, telling me what a great time they've had or how much they've learned and how much it meant to them to have been at this school at the times that they were. And so this has gone on for generations of students. So students have students who have been here. And so I really think so much of this is due to Leo. And I think, I don't think we really realize how much it takes to do 22 years. Does anyone remember 22 years ago? I mean, it's really hard, but this has been going on for 22 years, and that's a big thing. So thank you, Leo. And it's really an important thing for the community, for the whole condensed matter community.
Only to thank you, Sid, but I would add that it's really the students coming and participating actively in the lectures and the lectures that make us.
Yeah. And the other thing that I also wanted to say quickly here, because it's is that there's so much of this schism between hard and soft matter that's been going on in the community, and this place has been making sure that both sides get a good access to the time. So from that point of view as well, it's a very communal thing. Okay, so I have already given 2 lectures, and so I just want to tell you, remind you what it was that I told you, but also remind you why I'm telling you this. And so there were a bunch of different topics and that I've covered, different experiments. And the point was to cover experiment for this and to somehow give a flavor of the kinds of experiments that can be done in hydrodynamics and soft matter generally. And I've tried to pick experiments that kind of cover different areas. I mean, this was, I was assigned to do complex fluids. And so, I thought I would start out with the most complex one I know, which is electrons and graphene. I mean, how could anything be less complex than that? And but I wanted to say, well, okay, so we did show you this experiment, and all we were doing was using the same ideas as happens in a flowing of a river down a mountaintop. And the theory of this was, truly high school or certainly no more than first year college physics. And so you would have said, this is no point to doing this. And the point that I wanted no point doing the experiment. I mean, maybe the effect was interesting, but it was no point doing the experiment. The point I want to keep harping on is that the results seemed obvious, yet the experiment uncovered new physics, that suddenly something came into your face that we had to figure out why it wasn't behaving the way simple theory was supposed to tell us. And this is something that experiment does for you, even when you think, oh, there's no point doing it. the granular jet experiment hitting a target. Well, again, the point of this one was, well, there was some rather pretty phenomena associated with this, but it got to go across different scales. So it went from the tabletop physics of the experiment that I described, which was sand coming out of a tube hitting a target. But, oh, well, this is also quite similar in a lot of ways to a very different scale, which was the big experiments which were done at RIC on the quark-gluon plasma. And so, and this simple experiment actually then posed some interesting questions about what is a liquid, how does something come to equilibrium, what kind of timescales you need to reach that. Then the second lecture had the first two topics had to do with material failure. And so the first piece was just kind of in your face, huh, what's happening? That was the, which was that we just took this network, basically a honeycomb network with struts between the nodes. We stretched it and yep, it broke apart as rapidly as it could. So a good brittle fracture. But then all we did was we thinned down those struts between the nodes. And that was all. Everything else was exactly the same. And this thing, the time scale changed by 100,000 or so. And so this is, again, I mean, where does that come from? And this is something that was, you get to actually see this as a real, something that appearing in the experiment. It was, you know, I don't think we would have believed the kind of simulation stuff that we had done before this if there hadn't been this kind of experiment to show that this really is an effect in the real world. And so then going on to the Rifts and Rafts experiment, which is kind of part of this, was that you get kind of pattern formations, which are quite beautiful to my eyes, at least. But this was a model system, which we didn't intend to do anything like this. We just wanted to understand what was going to go on. But then you start looking at this and you say, this becomes a model experimental system, which we can study something on a very different scale. And so this is a cosmological expansion. It has a model that says, this is how you should look at this kind of a problem. And then the last thing I did 2 days ago was the inelastic gas. And say, okay, with this simple thing, you got to see that there are new universal laws that govern the relaxation of these systems, which these systems, we know so much about the elastic gases. The inelastic gases are something which are really, I mean, they're around us all over the place, but we don't typically spend much time thinking about them to the same extent. And so these are some of the things that I've been trying to stress, how you do the experiment. That is, you start off and then there's a problem, how you fix it. There's another problem, how you fix it, you pull this problem apart, much as you would do for any intellectual problem, and you peel it away until you get to the core. And that's, again, something that I hope you got the flavor of that, at least, even if that's not what you're going to be doing for the rest of your life. I hope that flavor has come across. But then the last thing I want to emphasize, and this is something which I feel rather passionate about, but and also I always feel, to even say it is slightly embarrassing, but the phenomena are beautiful. And that's why I love to watch them. I mean, and to work in this, and that should not be a shameful thing. That's why we should be interested in this stuff, and to look at this beautiful phenomena and get to try to be with it every day is, a fantastic opportunity. And so that's the kind of thing that I wanted to emphasize here for what these lectures are about, because unlike some of the other lecturers here, which were given a topic and they told you about this topic, my topic has been a little here, a little bit there, a little bit there. But what was the purpose of it? This is kind of, I'm trying to emphasize what the overscaling purpose of this is. Okay, so what do I want to talk about today? I want to talk about how does a drop break apart. Okay, so this is again. So this is, going from. I was told to talk about complex fluids. So this is ordinary fluids, and so it's not quite that, but complex is in the eye of the beholder, and so any fluid to me is complex. So that's why I'm doing this. Okay, so consider a drop hanging from a holder at the top, and initially it looks like this, and then more liquid collects and collects and collects, and finally it gets so heavy that the thing starts to fall, and this I have some liquid at the top, some liquid at the bottom, and it continues to fall once this thing has gotten large that gravity is pulling down more than the cohesiveness of the drop can hold it up. This thing is going to keep stretching, and this neck is going to, let's see if I can, something like this. This is the idea. I mean, this is a drawing of this, and what is the point about this? So something is happening that's quite dramatic here, which is that this is single, a single entity. This is still a single entity, and then a bit later, this thing is separated, and I have two drops, one at the top, or two patches of liquid, one at the top, one falling down, and they're no longer connected. And so there's a transition here. And this transition is, I get to say the word, I feel so proud of myself. It's a topological transition, right? And so here I said it, okay. And well, because it was a singly connected object, it became two separate objects, some fraction of a second later. Okay, so this is certainly a transition. The topology is not a serious part of this transition. I mean, it shows that it's there, but that's not the issue. The issue is something is happening as you go from here to here, and you get towards the end. And so what's happening is that if you look at this region here, that neck is getting pulled out thinner and thinner and thinner. Okay, so it can't, it keeps, as it falls down, this neck, this radius R, has to go to zero. And why does it have to go to zero? Well, if it weren't zero, it would be connected. Just the fact that you're saying this thing has disconnected means at some point along here, the radius of this thing has gone to zero. So what does that imply? And so that implies something dire is going on. And so what we know is the difference in pressure between the inside of the drop and the outside right at the surface, here delta P. That difference in pressure is just going to be the, it depends on the curvature of this. So it's the curvature of this liquid at that point times the surface tension. Okay, and so this is fine. This is just the Laplace pressure for this thing. That's something we know. But then if you look at the point where the radius goes to zero, kappa is 1 over the radius. Okay, so I mean, there are two radius of curvature, but I'm only considering this one for the moment. And so that one is going to zero. So that means that as R goes to zero, delta P blows up. Okay, so there's a singularity here in just the pressure flow, but not pressure flow, but the pressure difference. Okay, so this is a singularity, but there are other, if this was the only thing, maybe we could deal with it, but other things come along with it. That means because this pressure is getting infinitely large, the flows are getting perturbed by this, and the flows, if in many cases, are also going to just diverge as well. And so you have this real divergence in the problem. And so how do we go about treating this? Well, what we're, I think if you haven't been convinced by the summer school yet that solving the Navier-Stokes equations is a real mess and that it's basically impossible to do, then, well, the summer school wasn't as good as we thought. But that is the thing, is that we don't know how to solve the Navier-Stokes equations. And so how do we go about doing this? Well, we simulate it. So we put it on a computer and we get to some point. Now we get the neck to this size. So, oh, well, this is good. We're going, let's go. And now we want to go, but we haven't gotten to the singularity yet. So we want to go there. So we work a little harder. And we get to this point. And notice I say we worked harder because this thing is getting thinner here. I have to resolve that. But the drop is still the same size, so we have to resolve that. And so the difference in scales is getting large. It gets harder to simulate this. Okay, so you keep doing this, and I get to some point, and I say, well, I haven't gotten to singularity yet, so let me work harder. I work harder and I get a little closer. And then, well, I'm not there yet, so I work harder and get a little closer. And you can see where this is going. I mean, this is the Zeno's paradox all over again, right? I keep going and I'm going and going, but I never get to the singularity or past it. So how do I go about thinking about what is the, how do I get there? What do I mean by? Yeah, so you have to make the grid on which you're solving this smaller and smaller at some point, and you have to have scheme to do that. You have to make it go more and more of these scales, and you have to go from the tiny scales to the intermediate scales to the large scale. And so each time you get to a different thinness of that thing, you had to put more work in to get there. And so no, you get to that, you keep getting closer and closer and closer, but you get to the other side of this. But that's the great point. I mean, last night we had a rainstorm, and you look outside of the eaves of the dorm, and you see drops coalescing there, and they just fall. They're not, well, how am I going to do this? I mean, am I going to do Zeno's paradox getting to that point and so forth? No, they just do it. I mean, and so the fact that they just do it without thinking, whereas as physicists and mathematicians, so we have to think, well, how are they? This is this means that there's a lot that we need to learn to be able to get to that point and understand how do we handle singularities that occur in our equations. And this is a very nice one to do. Why? Because it, we can study it experimentally on tabletop. We can do simulations on it, and we can have theory on it, and the whole thing, all these different areas, push on this thing, and you get to some kind of a deeper understanding of this. And that's what I want to talk a little bit about today. And then the first thing I want to say is in the spirit of my crossing scales, and that this thing that I just told you about here is a drop. Well, maybe the drop is this big. I don't know. It depends on how much, what your conditions are. But typically, that's the size of this. You study on the count. But you get basically the same kind of problem at the celestial scale. And so this is the images from the Hubble Space Telescope of these star-forming regions. And to form stars, these big gas clouds have to coalesce into different regions. And as they coalesce, you have to get rid of the gas in between. And so it's the same kind of a problem. You get the same kind of mathematics going into solving this. The forces are different, the scales are different, but it's the same typical kind of problem. You also see this problem if you go down in scale. So you want biology, well, you look at bacterial colonies. They form structures, and then these, because they talk to each other. I mean, not with voices, but with whatever the bacteria chemical signaling that they do between them, and so there's some interaction there. It's not like the atomic scale here, but some interaction, and then those lines break up into blobs, and so that's the same thing. You had a line broke up into different regions. Okay, let's keep going down in scale, and you go back to the nucleus, which Niels Bohr told us should be treated like a liquid drop. And what the nuclei unfortunately seem to do is they fission. And so here again, you have this liquid drop at this tiny scale of the nucleus fissioning, and as it fissions, it has to break apart in much the same way as the same thing that we're doing here. So this is an example which I've covered many different scales, so you can see how kind of general this phenomena is. And studying it in one way where we can really get some understanding of it is a wonderful place to be. Okay, so let me start off with this problem. You heard about this I think, well, yesterday, it was, the words were said, I think, in Suzanne's lecture, but in a different context, I think. So if I have a cylinder of liquid, length L and radius R, the question is this cylinder stable or not? And well, clearly it can't be stable because we know that this thing is cylinder just going to want to collapse into one big sphere. So that's, I mean, we know that's what surface tension does. It tries to minimize the surface area, and the sphere has a small surface area for a given volume. Okay, so that's what you get if you allow that. But if I say, okay, no, I'm not going to allow that kind of behavior to take place. I'm going to hold these two surfaces this distance L apart. I'm not going to let L vary. So I have two surfaces that are wetting, that this thing is wetting, and so it can't collapse from there. And now I ask, okay, does that condition, is this liquid stable? Is this cylinder stable? And so the calculation is one that you've heard linear stability analysis over and over again here. So it's the same kind of thing. This is called, well, let me explain what you do is you so here is the cylinder, the original cylinder, and you ask, suppose I put a perturbation on this that looks like this. So I make a little bit bigger at the top, a little bit smaller in the middle, and bigger at the bottom again. So the walls begin to look a little bit like this hourglass shape. Okay, so this is the perturbation I'm putting. I'm just putting on basically that same R0 that I started with, but I have to keep the volume fixed. So that's why I have to, if it gets smaller in the middle, it has to get a little bit bigger at the two ends. But that's all. I'm just putting this kind of sine wave on this shape. And I ask, okay, is this area bigger or smaller than this surface area? Because that's what I'm varying in this case. And the point is that this area is smaller. If two pi r, that is circumference of this circle, is less than, oh, okay, I got the, it's small, yeah, so it's long, if it's long enough, it's unstable. So this is the, okay, so that means that once this thing has gotten long enough, it's going to start to squeeze in. So this is the Rayleigh plateau instability. Yeah, and
comes in perpendicular or something?
yeah, so that's all.
I strongly suspect that's critical.
Yeah, well, look, this is for this particular shape thing, and so I've just put a cosine on this. So yes, it's right. But once this thing gets longer, yeah. So yeah. So, what I'm trying to get to the point is that once this thing gets long enough, I can't stabilize this anymore. That's the point about this. And so this is just that simple calculation, how that would. Okay, now, what happens when it's like this? Well, we go back to what I just said up there. The curvature here is now getting larger because it's this radius is smaller than the original one. So this is going to start squirting more fluid out from the center in both directions. And so B is going out. So that means it's going to get less fluid in the center. And so it's going to feed back on itself. And this thing is going to try to run away from you. And so this thing really doesn't like to be here. So this is the Rayleigh Taylor instability. And I know maybe I shouldn't ask you to do this, but if you, at least those of you who are not wearing masks, how about that? Stick your fingers in your mouth and get some liquid between your fingers and okay, you are all very shy. And so I expected that, but we have a beautiful dorm. So tonight, when you go back to the dorm, go into the bathroom, lock the door. So all these other people can't see this. I mean, but then when you do that, go in there and do this experiment. And what you will see, if you do it carefully, is that there's a little thin cylinder of fluid of your saliva. And in the middle of that ball, that's the Rayleigh plateau instability. That is, it didn't want to stay uniform. It wanted to compress into the small little blobbiness, and that's a way of seeing it. So, you know, I knew you weren't going to do this, so I have a picture of this. So the picture is the bola spider. Okay, so the bola spider is this wonderful creature. It secretes its stuff. It doesn't build the web, but it secretes its sticky stuff. And the fly comes around, and it does something, and it then captures the fly, and then it does spidery things to the fly. But the reason I get to show you this is because I want you to just see this long thread of fluid, which is kind of what you would have seen if you had done this. You see what's called this varicosity of this thing, these blobs up and down this, which is just the Rayleigh plateau instability of this along this. And it's not completing because this is not a simple fluid. This is, there are long molecules in here which are keeping this thing from actually completely breaking, but it's enough so it can flow into these regions. So, you know, it's something that you see if you go outside and, you know, do on a real spider's web, and you see how beautiful that is with these little drops decorating the web. I mean, that's, you know, it's a beautiful thing in the morning, and that's the same thing. That is, they slide along the web structure, so just the water comes into these little balls. So that's this wonderful thing about about seeing this phenomena, and it's kind of really quite there. And one of the most fundamental of the fluid dynamics instabilities. Okay, so what I want to do is, well, where does this end up? This is the beginning of the breakup. How does this breakup end up? And so this is two pictures of the singularity of the fluid. And I have two things that I want you to note that let's look at the two things, and you can hardly see the difference between them, right? They are pretty, if I hadn't put this down here, I wouldn't have known which one was which, and they really look nearly identical. So what I want to do is to have shown this, I've covered up the rest of this drop so that I just isolated the part I want you to see is the same. And now I'm going to uncover it so you can see where they came from. And so this was the little bit you saw here. And they both look, when I just focused on that little area, they look very similar. And well, what are these? Well, this is just a drop of water falling in air. And so here it's hanging from the neck that is thinned down. And this one is actually, I turned this thing upside down, and it was this image that I just turned upside down, and I scaled it so they looked the same. But that one is the snap off up at the top. So why am I showing you this? Well, a couple of things. First of all, look at these beautiful images that I drew on the board. This stuff doesn't look like that at all. Something different is happening. It isn't this same old stuff as, oh, the cartoon of the teardrops falling from, that you get in the Hollywood version of a tear. That's what this was. This is not what this stuff looks like at all. It looks very different. That's number one. But number two is, well, look, looks like a cone pointing into a sphere. The cone is pointing down in the direction of gravity. This one is, again, a cone pointing in the sphere, but this time the cone is pointing up in the opposite direction of gravity. Gravity was the thing that started this whole thing off, and yet the singularity looks the same whether it's pointing with gravity or against gravity. Okay, so something universal is happening here. This is the first clue that, oh, it doesn't depend on some of these details, such as which way is gravity going. So things have fallen out of the problem as I get to the singularity.
Is it ever like this? Like if you look at, earlier before the singularity develops, is it ever?
Well, the very beginning is, this one, aside from the fact that it's not symmetric, which is my problem, is okay at the very beginning. It looks like that. This is clearly not right for water.
Well, but it's a question of scale, right? So there's some, if I look from back of the room, the first one will look like the middle, like the next one.
No, the thing is that what's different is that there's a difference in symmetry up and down here. The way I drew this one was kind of, it's the same as the down. It was just as proud. This one, oh, I've got this long thing, and then it starts to come out near the bottom. So someone was asking this about, I think it was Suzanne's lecture yesterday, was that where the things always happen in the middle. And well, this is the case. No, they don't happen in the middle. This is this one you see here is happening. Where it breaks apart is near the end.
So can I think of like there's a first stage where it's fairly symmetric and then it crosses over to this very symmetric?
Yeah. So this starts off. So this is the way it starts. I didn't include. I can show you the movie that we have of how this takes place, but it starts off as thinning down, and then as it gets longer, it no longer has this thing, and it gets longer, and then near the edge, the end, it starts to the asymmetry is certainly broken. Okay. Yeah, okay, well, we'll talk a little bit about that. I'm not going to, I'll say only a few things about that, but not too much. Okay. So, oh, yes, please. Oh, so this is just one drop falling. And so this is all part of the same experiment. Okay, so what we do is we have this drop. It starts off, it's just this little, baby drop. And all babies look the same. I mean, so it's, I didn't mean that. I mean, that was, but they look, well, I take it back. Okay, they all look, okay. And so this thing starts to fall, and as it falls, it stretches out into this shape, and then this breaks away. When it breaks away, this thing starts to restore here. That there's, I suddenly broke this thing. There was a lot of surface tension energy kept in that little cone. So that pulls back rapidly. It creates all these waves on the surface, and that's beautiful and gorgeous and all of this. But then at the top, it starts to coalesce. And then you get the same thing there as you get here. Where it breaks apart, it's the same thing. That's right. But it's the same thing. And so the point here is, oh, the way it breaks apart is independent of how you forced it. So, coming under gravity is the same as on a lake, the water being swept up and pushed away. The end point of this is going to look the same. Okay, so let's see. So what I want to now do is, okay, so how are we supposed to think about this? Or we're taught to think about this. And so this is the idea of scale and variance. Okay, so
what is the size of the drop?
oh, so the top, the holder there is about 1.5 centimeters. 1.5 centimeters, so maybe an inch as the scale of this. So that's the size of this thing. So it's blown up quite a bit. See here.
The next thing is that whole thing gonna break away?
Yeah, that's the next. So that's the second thing. And then if these things are oscillating large enough, some of those will break away. I mean, you can get various things of this kind happening. Okay, so what is the idea? So this idea of scale and variance, the idea here is that I made a big point of that radius going to 0 at the point of breakup. Why did I make that such a big point about that? Well, that means that that radius is getting smaller than any other length scale in the problem. Now, for me as an experimentalist, I am not worried about the atomic scale. Okay, so I'm just assuming this is a continuum fluid because I'm doing optics, and so I'm not going to be able to see below a micron in any case. Okay, so the idea is, okay, if this neck is smaller than any other length scale in the problem, the dynamics can't depend on any other length scale except the radius. So that's the statement. Now, so why would you even think that such a thing could be possibly reasonable? Okay, and so here's the thing I'd like you to think about. So you have water coming from rain on the mountainside from here in Boulder. It comes and it collects into mighty rivers that cross the continent and end up in the Gulf of Mexico in the delta of the Mississippi River. And in the delta, this big mighty river breaks up into smaller rivers, those rivers break up into smaller streams, into little brooks, into rivulets. And then finally, there's a flow between two little pebbles in that stream. Okay, and my question to you is, does the flow between those two little pebbles depend on the fact that the water originally came from the mountainside.
Might be some chemical content.
Chemical content, okay, but any other is, I mean, so the thing that I want you to see is, yeah, that, of course it can't depend on that anymore. I mean, the thing it depends on is it's flowing between these two little pebbles in the stream, and that's all that's left. It's forgotten all about that other information that was relevant early on, but not at this point. And so the idea is, at the end, you only remember something on the scale of that, the smallest length scale. Okay, so then you have that smallest length scale. And so what did that depend on? Well, that was created, in this case, because of the flow. The flow created that length scale, right? Which depends on the flow, which depends on the radius, which depends on the flow, which depends on the radius, which depends on the flow, depends on the radius, flow, radius, flow, radius, flow, radius. So what you're seeing is this, I mean, what I've just said for you is a fractal sentence, right? The flow depends on the radius depends on the flow depends on the radius depends on the flow. So it's smaller and smaller and smaller. And if I just take up some part of that and I blow it back up, I get the original sentence back, right? So that's so it really is a fractal sentence. And that's what that's what the math is kind of telling you is happening in this. And so how do we then begin to look at this? And so the idea is that you have this scaling form, which is that let me just write that. H of G and T. So is some function of T times a okay, so this is this kind of universal function, which is what's going to determine what that shape actually looks like at the end. But the way you get to it is Z is the azimuthal direction, and in this case, T is just the time that you're there, but that's also telling you about the horizontal direction. So what you're doing is this H in the region of the breakup. If I measure Z from this breakup point, Z minus Z0, that Z0 is where the breakup, all that this mathematics is telling me is I multiply the earlier solution by something in this direction that squeezes us down, but then I also have to multiply it by some other thing in this direction. So it's this similarity solution of, in the azimuthal, one multiplication, in the radial, another multiplication. They don't have to be the same function, but in this case, I'm showing it is, but this is that's the idea of what this does. So how do you do the experiment? Well, you take a very good images of this drop in the process of breaking apart. You measure Z minus Z0. So you're plotting the radius of this as a function of, this is the radius in this direction, and this is the distance from that singular point. And then you try to overlay these. And the idea is that if you divide by this T to the first power, so that this is the on both axes. So it didn't have to be the same on both axes, but in this case it is. You find this. Now what you find is as you get closer and closer and closer to the singularity, these start to all coalesce on top of the same function. And so this is the experimental proof that this is or it shouldn't be experimental evidence that this is the right way to think about this problem. That's a scaling problem around the singularity, and the singularity is so strong, it controls all the dynamics around that singular point.
You mentioned simulation at the beginning. Was there any hint of this asymmetry?
So there were various. What I want to emphasize here is that this part here is and this whole lecture is really not so much like I was trying to experiment, but no, this one is what I want to emphasize is, wow, we made a lot of progress on this because the simulation and the experiment and the theory all came together at this. And so at some point, the experiment was ahead of the simulation. Other times, simulation was ahead of the experiment. Sometimes the theory was ahead of both, sometimes behind. I mean, but it was this active collaboration between all three which really made this work. And so I want that to be, clear that this is not a battle. This is we're a wonderful, lovely group of people.
I'm just curious, when was that first realized?
The up down I think that was done. I think so. There were some images from Peregrine back, 20 years before this, that kind of showed how water was looking at that point. The understanding of starting this, to think of this in terms of the scale, that was a paper by Eggers and DuPont, the 90s. So, and we were following up on that work and then trying to see how this whole thing fit together.
How do you define H after the breakage?
So H after the breakage would have just then it would have had a different form, and so it would have still then been. I found out where where this broke apart, and then I would have had a piece on top, disconnect from a piece down below, and that would have been the breakage on the other side of this. And now I would have had a different scale. Those wouldn't have fit on this, but they would have fit on each other if I had scaled close to that point. And so I have two different forms what that function looks like before and after.
I can't quite understand the plot. So
Okay, so
let me just say what I do. So like the top part, that's the singularity development.
So this is the image of a drop, and what I'm plotting is H is the real radius of this drop from the central line. Z is the distance of any point along this from where this thing is going to come apart. And so what this is a picture of this region, right? And so that's what's happening. And then I want to say, oh, but is there a capital H in here? And so I do that by scaling, multiplying this by one number, this by another number. And the fact that I can get them to lie on top of each other is.
So, okay, so I now understand why there's two pieces to it, but it's kind of a spectacular how each piece is linear.
Yeah, so this one is a linear one. So, but there are other ones which are not linear. So some are, so depending, I will tell you about where that linear stuff comes from. Okay. And how worried I was going to be run. So this is for, so what was that fluid? That fluid was one liquid falling inside another liquid of equal viscosity. And so that was this image. But if I then change the viscosity of these things, the point is that, each one of these things has its own shape, but the scaling is the same in each case. That is, and you can get this stuff to scale on this as a function of the, so varying the ratio of the inner to the outer viscosity, which is this lambda, I get different curves. And it turns out the one where the equal viscosity is the worst one for getting the collapse. The other ones collapse a lot more easily. So that was. So this is the same parameter as the one before. So this zeta here is z minus zc over tau. Okay, so the point I want to now is, okay, so you kind of were asking about this in some way. I don't know if this is what you thought you were asking, but this is what my answer to what I think you were saying is, oh, well, there are a lot of different universality classes in these things. That is, I told you about this in the simplest case of, the length scale goes to 0, and so it depends on nothing else. But there are a lot of cases where other things go to 0 also. So, for example, in the case of, I could have the viscous length scale go to 0, and that's below the region. And so what I get to look at is in the region of, above a micron. And so that is not in the asymptotic region of everything going to 0, but it's another asymptotic region where I've set the viscous length scale to 0 before I start doing the experiment. Or I could have set the capillary length, various things to 0 first, second. And so I can move these things and look at different universality classes by varying different aspects of this. And so what are the aspects? So this was the water in air that we just saw. And so that's water falling in air. This is a different drop. This is water with glycerol added. So glycerol is the fluid of choice for so many things that you want to mix with water and it changes the viscosity. It completely goes from water to 1,000 times water at pure glycerol. McDonald's uses it to go from, milk to milkshakes. I mean, it's that's what they use it for. And so what you see here is, something different is happening here. It's got this, it goes unstable to this thin thread, which then you can examine. Yeah. Surface tension varies by maybe 10%, but the viscosity is varying by 1,000. Right, so that's the difference. And so this is one with 100 times the viscosity of water. This is the one I just showed you. This is pure glycerol in the middle, silicon oil on the outside of the same viscosity. And this one is water in the middle with a very, very viscous outer fluid. And what I hope you can see is that's still connected in that thin thing up at the top. Can you all see that if you get close, you can see that's still a thread connecting it. And I just find it amazing. Oh, this is how nature decides to have a drop break apart. I mean, it's just doesn't seem the most efficient thing for nature to do, but she doesn't care. Okay, so this is how we get, as an experimentalist, I get to vary the viscosity, the inner and the outer fluid. I can vary the density of these two things. I can vary the surface tension, and then I can vary the nozzle diameter. And those are my tools to get me into different regimes, much as you would do this in a phase transition experiment, where you would vary different materials to get into different classes of what kind of spins you have.
So one question is, how small a scale can you resolve? How small a scale have you studied?
So for these studies, when I'm doing optics, which these are all optical studies, this is the small scale I can get to is on the order of a micron. But if we need to go smaller than that, which I hope I'll get a chance to mention one thing, well, then we use electrical current, and that I can, I'm just measuring the current going through this region. So I have a current from here through there, and I can measure what the flow is, which would be dominated by that. So that's another set of things. So that can go much smaller.
So those really small scales, do you see any role of thermal fluctuation playing a role?
Okay, so just a moment. Okay, so just for your delectation, Leo. Okay, so here is an example. Okay, so this is the one I just showed you. This is viscosity, of the inner viscosity is glycerol plus water. That's the one I showed you. And this is in air and the outside fluid. So this is one where all the terms seem to matter. And look at how this breaks apart. So you get this long, long, thin neck. Doesn't look like any of the stuff I've shown you before. And then it goes unstable to make this thin thread here. And so we think that that's what the answer should be. And so this is a blow up of just this region. And we look at that, and you can fit this scale here to the kind of, a similarity solution type of thing that I just told you. But then, we looked at this and said, gee, this happened once. Well, could it ever happen again? And so then, and this was not what was supposed to happen. You look at it a little bit later, you see that this thing then goes unstable to an even thinner thread. Okay, and so being physicists, it's happened twice, so it obviously happens an infinite number of times, right, on the way to the breakup. And so that the analysis of this had to come later, because this is not a linear thing. This is because tiny little fluctuations on this neck could drive another instability in. And so that's why the neck forming regime is coming in. So that, I hope that answers the question. Okay, so
Being in the computer room, a bunch of burner, writing my own stuff, and he was doing this stuff. And
yeah,
he was complaining about round-off errors in his code. He was trying to understand whether his code when he started seeing something physical, unphysical.
right. And we were doing the same thing. We were trying to figure, is this optical artifacts or not? And the first stuff we saw were just optical artifacts. So we worked harder, and it was actually there. So, now I want to.
If you have a liquid drop inside a two plate, and if I pull it apart, you can see a neck forming.
Yeah. So this, yes, you should see this kind of behavior. Well, I should say, you should see this behavior independent of how you're doing it as you're pulling it apart. Whether you see all this other structure, that depends on the boundary conditions and everything that you put in here, and that's not what I'm telling you about. I'm really focused. I mean, I want you to see that because I think this is lovely photographs to look at, but the stuff that I'm really telling you about is just this region, and that should be universal.
My next question is, if I can see, then this neck formation, that neck is stable. After a long time, can I see this is?
No, this is going to be running away from you. That is, this is not going to just sit there. This is very dynamic. I mean, so this stuff is, the flow is coming in here, and the flow is dominating this thing. So it's going to, it's not going to just sit here and wait for you to do something. It's not quasi-static.
How much is spread on the right compared to this part?
Oh, geez. What I remember was this is kind of on the order of 10 microns. And I think this stuff was on the order of 100 microns or so. So that's the scale that I'm remembering, but I wouldn't trust exactly what I'm saying here. But I think that's the scale of which. So these were done with high-speed cameras, right? Okay, so this was done with, well, no, the movies were done with high-speed cameras. These, to get this quality stuff, we had big cameras with very, very fast lighting. So the time scale for the light was, I think it's on the order of a microsecond is what we had, as I recall. Okay, so just to push this a little bit further, so we saw this behavior. This is the water drop in air. So water falling in air. So, clearly, suppose I just reverse it. And so what would the reversal of this be? Well, suppose I have a air drop in water, otherwise known as a bubble. Okay, so I've just changed what was on the outside, put it inside, and the inside, put it outside. Okay, and so this now is going to be a movie, which is what Leo wants to see, something that satisfied his inner thing for symmetry, right? I think that's what you want to see something. So let's see what this movie looks like. Okay, so that one did look quite symmetric top to bottom. So let's do this again. Okay, so you can see, and you'll see that the little drops of launch in the middle here that fall up here. Once that go past there, it's going to hit the top surface. There's all sorts of neat dynamics in there, but this looks different. I mean, it's not the same as the drop in air, water drop in air. So something very different is happening. And what I should tell you is that this was a very carefully done experiment. We made sure this orifice was really circular. We really tried to level this very, very carefully to get all of this. And we were trying to get this thing to be pristine to see this. Why am I telling you that now, whereas I didn't tell you that about the other things? I mean, it wasn't that the other things were done sloppily, but the things I didn't need to. And so the point about this is that the first person who was doing this was a master's student, and he would come in showing me the pictures that he got in this thing, and he said, "Gee, I'm really so," I say, "It doesn't look symmetric." And he was, "Yeah, I'm really so sorry, Professor." They called me Professor. I love it. I worked so hard, but none of them ever look symmetric. But I try to give you the most symmetric ones, and no, that's exactly the wrong. That's nature was what nature was screaming at us right then was, no, it isn't symmetric. By only making this really, really carefully, not breaking any symmetry in this, were we able to kind of coax the symmetry to be this way. But if we took this thing from, go the other extreme, have this slot nozzle and eject the air quickly through here. So this is now just the section between the liquid on the top, the bubble on the top, and the air coming out of here. This is what this thing looks like. And so that's very different. That is, it didn't have that symmetry. That symmetry wasn't there. It was only, and so something very different is happening in this kind of a phenomena. And so let's see if I can stop it. Oops, no, it doesn't. Okay, but you can see that it looks much more like a tearing phenomena than a necking phenomena.
What is the time scale ordering difference between them or their poles and
So there, the falling of the drop is fast because it's just in air. The air in the water rises much more slowly because that's you've got all that inertia of the water to get in. That's not the thing. The thing that's important for us is how fast do we have to film this in order to get this behavior. And so in this case, this is, we have to film this faster than we ever had to film the water. And so it's a different scale for that. So, and so this is where Wendy Zhang and her student Laura Schmidt came in with a theory of this, but it was saying that the fluctuations, if you start off in an asymmetric system, those fluctuations never die out, even though the radius of the drop is falling. And so this was a tour de force experiment by Nathan Keim that showed, okay, he could resolve between one direction and the perpendicular direction of that drop, something on the order of a few microns change in the width of that drop from one side to the other. It's a function of time. And you can see that here, the breakup event is actually something in the middle of this neck as it thins out in one direction. And so you can see those kinds of features coming in, which were not there in the water falling in air case. Okay, I'm just going to show you some pictures of this part so that, but this is now another thing that you would have said, oh, this is the opposite experiment. So this is two drops coalescing, which again, if you think of that, that's also got this thing where they just come together and then at some point, when they just touch, then they start to expand. Right? And so this is what's happening here. So this is one drop being, below, another drop coming down from on top there, being ejected ever so slowly from the top and bottom, so they just touch. And then we're going to see what this image looks like. And it was thought, well, this is also just like the other one, just opposite. That is, the other one I was breaking apart. Here, I'm taking the same fluids now and bringing them together. And what you see is, oh, well, this doesn't look at all the same. And so this is, so this is the phenomenon that you see in this case. And so this is the one that we could not analyze well enough just from the optics because of the speed of this. And the reason the speed is because the connection is this curvature in the way, not this one. And so that's really putting this thing apart rapidly, and you can't see in there so well. And so that's, and so this is the one where we actually did it with two electrodes from top and bottom to actually measure how that the neck started to form and you get the dynamics in that range. I won't go into this more than to just say, okay, by analyzing this, you see that you have a phase diagram for how coalescence starts, and actually this is the one that the theorists had, and then you start looking at that carefully, and you see, it's completely wrong. Unless there was this kind of connection between the theory and the experiment, you're very apt to not get the right answer. So I'm not going to go into that because I want to spend the last few minutes talking about another problem. And so this is the problem of splashing. And so the question that I have is there anything interesting in a drop hitting a plate? And so this is another kind of phenomenon that is it's going to hit at one point. Maybe that's a singularity. You can think about it in that way. But before I even get to that, I just want to, okay, this is a violent collision, right? I'm having this drop that just falls and it hits this surface, and then of course it's going to splash. So what I want to show you first is just a movie of this. Okay, so this is a drop of alcohol. Okay, it's a small drop. It's about 3.5 millimeters in diameter. So it's a tiny little thing. It's falling in air onto this smooth, dry glass microscope slide. You can see that it's kind of gray here. That's the area. And so it's falling from roughly this height. So it's going to be hitting this slide at a meter per second type of velocity. That's the scale at which it's going to go. And as you see this movie, you will see two things. One is that you're going to see the reflection of this drop in this plate below, just because it reflects. Second thing, you see that white thing in the middle. That's just the lighting. It's not that the drop has a hole in it. It's just that we have the light source behind this, and so it acts like a lens. So let's see what this looks like. So this is just a movie of that. So it's coming down. So, I mean, it's, it's rather nice. I mean, and so I want to see it again. So let's see it again. So as this thing hits, you're going to see it immediately starts to move out on this plate and start to create this corona, and that corona is just going to be breaking up. So here it comes. Pow. It does this. Okay, so why does this thing splash? What controls the splashing? Well, one thing is clearly how fast this thing is falling and how big it is. So if I took a tiny little drop and I carefully laid it on the table, it would not splash. A bigger drop, you know, a swimming pool falling is going to splash all over the place, right? So it's the velocity and the diameter of this thing is going to make a big difference. The other things I told you about, the surface tension, which was holding this drop from moving, that's got to make a difference. The viscosity, how easily this thing flows, has got to make a difference. And now I've told you everything you need to know about a Newtonian fluid. And so this that's it. Okay, so what else do I need to tell you? Well, what's the substrate? So the substrate is it hard or soft? Is it smooth or rough? Is it wet or dry? And now I think I've told you everything I need to tell you about that microscope slide. Okay, so that's it. Well, I guess I didn't tell you about the air because, you know, the air clearly is unimportant, right? I mean, the air is 1,000 times less dense than the liquid, 1,000 times less dense than the substrate. I don't feel it as I move my hand around. But I guess I do know that if I stick my hand out the window of a moving car, I feel drag. And so all these little guys here are trying to out, and they're feeling drag that holds this thing in place. So if we somehow got rid of the air, we'd be able to make a really big splash. Right, that's the idea. So that's what we wanted to do, is we wanted to see, you know, how big a splash could we make. And so here it is again. So this is the third time you've seen this movie. And then we'll play this movie. So let's see this one first. Okay, so you've got that into your mind. This one, we have taken a third, it's a third atmosphere. So 2/3 of the air is out, basically. So this is the atmosphere you would get at the top of Mount Everest. So, you know, you could live there, you might not be happy, but you could live in this container. Everything else is about the same. That is, we have the same alcohol, same drop, same diameter, falling from the same height onto the same smooth glass microscope slide. We only have this in a container where we were able to take out some of the air. Okay, so now we want to look for this big splash. So here's the big splash coming. So it's coming down, it's going to hit, and now you're going to see big splash. Okay, so look, I knew it was coming, but what I told you was not a lie. What I told you was what we really expected to happen before we did the experiment. Okay, so we took away the air, which was supposed to make it possible to have a big splash, and the splash disappeared, completely gone. It just spreads out smoothly on this surface. So, I mean, to show the fun of the experiment, we started laughing hysterically for about 3 months before we realized that we had to get back and actually study this thing. Okay, so this is the what we had to do. But it was really a case of Aya Rabi's thing, victim of who ordered that. I mean, you know, this is not exactly the opposite of what we expect. One of the things that you could ask as well, you know, if I now drop this drop from a little higher, it's going to be moving faster, and therefore, oh, it will splash more. So I stop this from splashing by taking the air out, but if I move it high enough, it'll begin to splash again. So we studied that, and this is the kind of behavior that you see. So this is the velocity at which it's hitting the plate. So that we just get by the height that we drop it from. We measure it also, but its gravity is pretty uniform. So this is tuned just by the height of the dropper. This is the pressure in the container. And it is kind of what I said, that is that if I go to high velocity, I to go to very low pressures in order to stop this thing from splashing. Right? And if I lower the velocity, then I have to increase the pressure in order to get the splash. So I have something that's going down in this way. But notice this is not a mistake. So if you want reentrance, here's reentrance for you. That is, if I sit here at 35 kilopascal and I start up at the top, at high velocity, it's splashing, it stops splashing, it starts splashing, then it stops splashing again. Okay, so this is, that's real, yeah.
How do you quantify splashing? Is it like an abrupt splash, no splash, or is there a gray area?
So there's, it's abrupt in the following senses. I want to ask, is something ejected? Again, but then you can ask, well, how much is ejected?
Yeah.
And so in some studies that, not in these particular, but the ones where we had more viscous fluids, we counted the number of drops coming off, and it does, the number of drops gets smaller as you approach this transition, but it's still dropping, and then below it, it stops. But there's fluctuations in that, and there's parts of that we don't understand. Okay, so let's just take a look at another drop. And so this is a more viscous drop, so 10 times higher viscosity than water. So it's water glycerol mixture. So we let this thing fall, and just an ordinary atmospheric pressure. And okay, I'll stop it here. I mean, it's clearly not going to splash. It's just moving out, right? So splashing stop. Okay, so let's just continue this movie and finish it up. Man, I lied to you again, right? Even though it started to move out smoothly on this surface, it still was going to splash. So the morphology of this splashing behavior has completely changed. So does it still matter whether the air is here? And so then what I'm going to show is just the same liquid now at lower pressure, and this one, we let it go, and it stops splashing. So the air still matters, even though the morphology of this whole thing has changed. So there's something fundamental about the role of air in here that was totally unexpected. Right? The air is the control parameter. I mean, just to point out, that people have been we could have done this even without the high-speed cameras, right? That is, you can just ask how much splashing, just put ink in the thing, and you have paper surrounding it. And yes, is the paper getting wet with black dots of ink, or is it dry? And you could have done this at different air pressures, but no one ever did this because, honestly, it was too stupid an experiment to do. Right? Obviously, it wasn't going to work. Obviously, it couldn't make any difference for all the reasons I told you, and also the other reason is that the viscosity of a gas doesn't depend on the pressure. So even though I lowered the pressure, the viscosity of the air around it didn't change. So why should that have mattered at all? So for all these reasons, it wasn't the right experiment, but doing the wrong experiment produces good stuff.
What's the size of the ring?
So that there's been some work on this, which was done by Christophe Josserand and I forget who his colleague was that was working on this, but they were looking. So it's how much is this thing flowing out? So you have to ask, what is the viscous damping as this thing moves out of a thing of a certain thickness? And so how far out can that go? And I mean, so that's the calculation. And was there a simple law? I forgot whether there's any simple law that you got out of that, but those are the considerations that come in, is how this thing, how easy it is to flow of a given thickness of the fluid, because it all has to get out there. Okay. Forget this. And so then I just want to end up with the last few things. So this is asking, okay, so we can do things like ask, what does it matter? How does surface tension matter? How does viscosity matter? How does, well, any of the parameters go? And so we spent a long time doing that. But the other question you could ask is, well, where is the air making a difference? And so this experiment was done by Michelle Driscoll. So what she was looking at is looking underneath the drop. So the drop is coming down. And so this is the center of the drop. You're going to see this hitting the plate. So basically, you're looking up and it's coming down. And you're filming this with an LED, which is basically a monochromatic source. So you're going to be able to see interference fringes from this. And so that was the idea. Using interference fringes, we could see how thick the air layer is under this as this thing spreads out. And so this is what she saw. And so I stop it here, just continue. But you can see, in the center, there's a little divot. So it trapped some air in the center here. And the rest of this is black. Black means that the thickness of that, of the air layer that's there has to be less than some very small amount in order for this thing to look dark. And so we can analyze how much that is. And it's certainly can always going to be consistent with touching the surface, but this is so small that the conclusion is that it really is touching the surface. That's the scale of which this goes. And now we continue this a little bit more. So there's just continuing the same movie, and you can see what happens. And so now you see, as this thing lifts off, you see all the interference fringes around the edges of this drop. Okay, and so you can see that, and it's the fact, look, this is on the order of millimeters. Difference between fringes is on the order of microns, right? So it's really a very small angle at which this stuff is raising off the surface. Okay, so this is saying, okay, and you can see that thing in the middle is really the air bubble, because you can see, if you look in that, you can see the interference fringes in there. So it really is the shape of this underscored thing. Okay, so now, so the air is not underneath the drop doing anything. I mean, the thing only starts to splash long after the air has, there's whatever's in the center is gone from the edge. This is all touching the surface. So there's no air there. So it's not the air under the drop that matters. So the last thing I want to show you here is visualizing the air above the drop. And so this was done by Irmgard Bischofberger, who is a postdoc in our lab, and Kelly Mauser, who was a RU student there a few years ago. And so this is a different kind of photography. This is the drop falling in air, and this is the substrate. Looking at it side on, but this is what's called Schlieren Optics. And so for those of you who are unfamiliar with Schlieren Optics, this is a kind of way of emphasizing very, very small changes in the index of refraction. Okay, so I don't want you to look at this. This is going to be dark and black and uninteresting. The drop is going to be small, dark and black and uninteresting. It's the gray area around this drop, which is what I want you to be paying attention to. And so, look, it's the idea is if you look at a hot roadbed in summer, you see it's all shimmering as these heat plumes rise from that surface. And what Schlieren Optics is basically trying to do is capture that in as crystalline form as possible. So that's the idea. So we're going to be looking at what happens to the air around this drop. So to give you an idea about this, I just stop it here. And what you see is, okay, so this is a drop. As I said, dull, black, uninteresting. This is a substrate, dull, black, and uninteresting. But in the gray area, you see there's a lake that you can make out behind this drop as it falls. And so this is the kind of thing I want you to be looking at for the rest of this. So now I'm going to play the whole movie through so you see what you should be focusing on. So here it goes. Okay, so that's what the air is doing around the drop every time it drops. And I wanted to end with this because this, to me, is one of the best movies we've ever. I didn't take it. Irmgard and Kelly took it, but it emerged from our lab because it's just, such a quiet, elegant thing that's happening every time this drop falls. Unfortunately, Irmgard was able to analyze this, and even though you think, oh, these wonderful vortices are there and they could pick up the edges of the drop, that's not, it's not enough to do that. And so this is happening, but it's not the cause of what the cause of the drop splashing. But what I wanted to end with this just because I think, this is the other part that I kept telling you I wanted you to understand about the experiments is that, it had this question of reach, it asked new questions. It could transcend scales of the kind of phenomena you get to look at. You get to peel apart an experiment one part at a time to try to get it to the point of, understanding what it is that, making the experiment tell you what the experiment is to tell you. It shows surprises of things that you didn't expect to happen, even in experiments where you thought it should obviously work, but then new things occur. And so, that was one that I showed for the Hall effect case. That was something you came in. But here, the whole idea that the air mattered for the splashing was not something that was expected. But the last part that I had in red at the bottom of that first slide was that these phenomena are beautiful. And so I just think that this is a case of that. And I guess that's what I want to end with. And so I should then, just before I stop, I want to put up pictures of the people who did all this. And so these are the cast of characters who actually did so much of this work. The top row are the people who worked on the drop breakup problem. All of these people are the ones who worked on the splashing problem. Kelly and Irmgard were the ones who did that last movie that I just showed you. And all of these people did different aspects of what I just mentioned. Well, that's it. So that's what I wanted to get across. And I hope that these different lessons that I wanted to emphasize about experiment was able to be illustrated by some of these experiments that I showed you. Okay, thank you very much. This one? Okay, so the way that is set up is so I have a points, basically a point source here. It comes out into a lens. This lens collimates it to be parallel light. And then it comes through another lens, which then focuses it to this pinhole. But at the pinhole, what the way this does is I have a knife blade that I take up into the focus point. And so what this does is, so where is the drop falling? The drop is falling here. Okay. And so what we see is if there's any change in the index of refraction region, it tilts the direction of this parallel light a little bit, which means it's going to fall a little bit above or a little bit below one side or the other. And if you didn't have that knife blade, you'd still be picking up the same intensity. But because you have that knife blade, it's able to take, oh, if it goes down, it gets dark because it's being cut off by that, by the knife blade. And if it goes up, it gets brighter because all of this stuff is now getting into the region. Is that what you, that was the question, this is how you do the Schlieren optics. So this is, and I always thought it was named after Mr. Schlieren, but it's actually Schlieren just means, it means something in German. Who knows, what does Schlieren mean in German? No one, okay. It means something like tear or something. It's is that, you're nodding, is that right? No, you don't know. Okay, so anyway, so that's the, it's not named after a person, but it's named after just a technique. Yeah.
I'm interested in what constitutes the trajectory or the wave. Is that the evaporation of the drop? Oh yeah, this.
Okay, so so you want me to just want to see that shadow? Okay, so so what's happening is, so in order to visualize this, we had a bunch of different things. One was that even before we did anything, there was a bit of this because you're disturbing the air around it, and that gives some density fluctuations in the air, so you can see something. But what we did around this also was we had some glycerol on some hot plates. So the glycerol was evaporating, so there was heavier fluid. Glycerol has a different index of refraction than the air. And so when these things mixed, you got to see better what these lines were doing. Okay, so it's so it isn't just the air. It is air, but it has some of the vapor in it, so that enhances the experience. Yeah.
According to Wikipedia, Schlieren means streaks.
Streaks. Okay, streaks. There it is. Good, thank you.
Visualize instead of our drop, if I draw what kind of structure?
So there's a lot of you can drop a lot of things. So you didn't ask, well, how come? Where is the splash in this? And we were able to get rid of the splash because there's some other things we found out about splashing is on that movie that I bypassed, is that if you slightly roughen your surface, you can actually make it stop splashing. So this was done on a case where you didn't have any splashing. And so you got to see these convection rolls of the air just coming up around it in all these different ways. But if it was splashing, then you get to see that with these bits of sparks going through, which are the drops that are dragging the air around it. And so that it's exciting in a different way, but it doesn't have the quiet beauty of this. If you dropped just a ball, you would also see things moving, and you would see convection rolls. So we did a bunch of these things. So it's having to do with you're dragging this air, and then it hits the surface, and then you suddenly all the air that's being entrained with it is being forced to move out quickly, and that's what is giving rise to these flows. The trouble with the ball is it tends to bounce, in which case then you don't get to see it as well. But that's the
Getting back to the droplet experiment, just to have an idea if I'm getting the right feedback from the viscosity, right? So when you increase the viscosity, your net gets much longer, right?
in these cases, yeah. I mean,
and that's in many cases because like increasing viscosity, so increasing a lot the time of relaxation of the fluid itself. However, you're not playing a role on the capillary forces, which drives the instability, right?
Okay, so but the way I like to think about it is that if I were to set this up with, let's say, I write down Navier-Stokes equations for this thing, and I ask, okay, if something is diverging, something else had better be big in the equation, right? There's things have got to balance. If there has to be something big over here on the other side to make it work. So we put a little meter on each of the terms as which ones are getting big versus small. And so the whole point of doing our, choosing these different fluids, and so I should say, I think I'm answering maybe, and I realize it, answering a slightly different question. I'm asking what's happening right at the singularity. I think you're asking kind of what is the larger scale shape of the drop, which is I'm talking about. So I realized suddenly that maybe I shouldn't, but this is the part I know. I mean, I don't know, to get the large scale shape of these things is at some level, it doesn't have that same problem of how do we resolve a singularity, but you do have to worry about the shapes and how the flows along this take place. So so what can I tell you? So for the water, we got this breakup, and then we got these beautiful little undulations along this. Why was that possible? Well, that was possible because the viscous length scale of water is atomic scale. It's so small. So viscosity doesn't play a role, and so the only thing that matters is the surface tension, the capillary length force moving up and down. So on this, as you go to the other cases that I showed, you don't get that because the viscous length scale goes as eta squared, and so viscosity squared, and so changing this by a factor of 100, you have 10 to the 4th larger scale, and now that competes with the capillary thing, and that dies out. It means I'm not able to have that kind of behavior. But that's the same kind of thing. The way we set this up is we try to look at what are the different scales that you can have in this problem, and one of them is this viscous length scale, which is saying on what scale is the viscosity going to matter in competing with surface tension, and gravity. We know that is given by I kind of said that the other day, the Bond number, which is the gravitational forces versus the surface tension forces. The interesting thing about the case of the air bubble is it's not governed by any of those things. That's governed just by the inertial collapse coming in, so that it doesn't care about the surface tension. I mean, I was really astounded when I was told that. I thought it's got to depend on surface. No, what drives that is just the pressure field, the inertial collapse inside this bubble. So those are the considerations, but then exactly how one versus the other manifests itself is would need a calculation to actually show what these figures look like.
I was just wondering if you have a link to, you know, these beautiful movies over the years where it's assembled somewhere we can watch them.
Yeah, so a number of them are on our, are they on our webpage? Yeah. So some of them, could be, but there's what does exist is on our webpage is a talk I gave where I was just trying to talk about the beauty aspect of this, not about the science. And so that's actually shows some of these movies in that. So that's on our webpage. On my.
But it's not like there's, you know, this, you know, covers many years of systematically studying.
Yeah. No, so I don't. So we don't have collected except in these talks, and so that was a talk. They are on the okay.
Okay, thank you.
You ever seen FT not linear T? That's a different
Oh yeah. So the one that the one has the neck forming neck regime that has a T squared in one and T in the other. And so, but that was before the neck forming neck part. But that was the system in which this analysis would have said it's not linear in T. One is T squared, one is T. And water in air is T to the 1/3. So that's so these things. I mean, the T1 is just the one that was the one that we were able to really nail it as the best we could. So that's why I showed that.
I was just curious for the next behavior. There was quickly flash at phase diagram. So there's some phases where there's a phase transition. What happens the next behavior after the interesting happens?
So you're saying for the necking. So that is as after the thing breaks apart, is your.
Right. Because you had like as I changed this dimensionless number, you go to different regions. And so like what happens if you sit right up?
Then okay. So I'm sorry. Okay. There were two questions there. One was that if it's a singularity and it's obey all the things that singularities are supposed to do, that means that I would still get the same length scales and time length versus time scales on the other side. It's just that with the different forms for they're moving towards different directions, so that it separate in the same way that the neck is moving before. But so that's just a question of analyticity, I guess, of the equations. But if you say, oh, if I move between two universal things, all we're going to see is a crossover regime. That is because you know it as what this is kind of saying is the way we set this up is, oh, if I just kept going down and down and down and down in size, which you could think of doing, but we can't do in experiment. This thing would go from one regime to another regime. And so when you say, oh, well, it's like a crossover, so that I'm looking like I'm getting the exponents for this regime. And now, oh, I'm in a different regime, so I start getting exponents for another regime. And there's a crossover region where, oh, it's clear that one size is really beating out all the other sizes. So that's the, I don't know if that answers your question. But
In terms of.
yeah, let me, and then. No, I mean, so I'm not quite sure what that would be or how you would do it, but certainly I haven't heard anyone else thinking of doing that either. So.
terms of this splashing, I mean, I'm not sure I saw a conclusion, but the air, you think it's the thicker air we're getting underneath?
No. So what I think is that this thing comes out and it starts expanding. Well, it'll just expand forever. Why should it ever push up? I mean, why? And so the splash depends on it leaving that surface. And so why does it leave that surface? It's because it's being pushed. The stuff is being pushed into the air is pushing back on it, and that lifts it.
It's also the idea of getting in on
But just at the lip, not it's not coming from underneath, but it's trying to move into this region. And so if you go to the famous pictures of Edgerton of a drop into a pool of liquid, you see these beautiful crowns. Well, that's because where is that coming from? That's the drop coming in, pushing the stuff out, and the whole thing is rising. And it's the outside air, which is outside liquid, which is predominantly important for that stuff coming up. And so here we don't have that. So we just have the air. So if you take the air away, there's nothing to be done. So that means you can never have splashing on the moon. Maybe on Mars, but not on the moon, because there's no atmosphere on the moon.
Maybe with this, time is running short.
Yeah,
we
we
should
should-
break for coffee.
We should test tea droplets on that.
Okay, good.